Welcome to Manufacturing Explained. My name is Greg Paulsen. I have spent my career using various manufacturing technologies to produce and deliver engineered parts. Manufacturing Explained is an expert-to-expert conversation on all aspects of manufacturing. Today, I'm joined with Scott Benson, a senior project engineer at Xometry, to talk about injection molding, specifically that path from raw material to parts. I always think of injection molding as the ubiquitous mystery of manufacturing. It's one of the most common manufacturing technologies for producing parts, yet is often seen as intimidating for those learning about that subject. Right now, you're probably staring at 100 molded parts. Whether it's on your desk or dashboard, most plastic parts you see are injection molded. How are these made? What's the journey of plastic injection molding? Stay tuned for Injection Molding Explained. Injection molding is the most popular way of producing plastic parts because of high repeatability, high customization, and low prices over quantities. I'm here with Xometry injection mold engineer Scott Benson to talk shop and get answers about manufacturing. We'll be talking about the injection molding process, the machine equipment, mold tooling, and how great parts are made. So let's talk plastics and what the injection molding process looks like from the material's point of view. I'm interested in following the material from its raw form to the machine and ultimately to the mold where it becomes a part. So Scott, thank you so much for joining on Manufacturing Explained.
Yeah, glad to be here.
Let's get some background. Scott, can you just tell me a little bit about yourself and how you got into manufacturing and your molding experience?
Absolutely. So I have a mechanical engineering degree that kind of laid some groundwork from fundamental standpoint. I've carried many various roles in injection molding fields. Anything from being a quality manager of an ISO 9001 certified quality management system to being a project engineer along with lean manufacturing engineer through a few different molding plants over the past 13 years. So about 13 years of experience. I've seen many different types of tools, many different industries or end uses of parts, multiple different materials. So it's been a pretty good adventure.
No, it's awesome, and it's great because speak. We're both at Xometry and speaking internally, and I know that you're also like have amazing words of wisdom when it comes to molding. So it's always great to like bring experts on and just talk more. Uh, and I think one of our goals is to look at molding from a bird's eye view. So we want to cover a lot of different topics in this field.
Mhm.
But today I want to essentially focus on the materials journey. Taking that raw material, what is the raw material, right? Just going that level, and then walking it through the machine. As we're doing that, though, maybe it may make sense to break down like what is the injection molding process. So if you are giving the elevator pitch, or maybe a long elevator pitch of like what the injection molding process is, could you kind of walk that through for in more layman's term, like if you're
Yeah,
speaking to an engineer new to the process? Yeah.
absolutely. So we're going to basically take raw resin pellets, plastic pellets. They look like little BBs. We're going to feed them into the hopper of the machine, where the material will go down what's called the throat of the machine. It goes into what's a screw and barrel, which is a heated screw barrel system that is kind of like an auger bit that pushes the material forward. It creates a homogeneous melt, and then it will be uh, held up in front of the injection nozzle, where it will be injected into the steel mold under high pressure, and you will hold that pressure to the plastic part, to the cavity of the tool, until it is hard enough to eject. Then the mold will open and the plastic parts will fall or get picked out by a robot.
Yeah, absolutely. So like in this injection molding process, I think the magic is you have this raw material and you're talking about going that cavity.
Mhm.
And in this case, the cavity is essentially the negative, the shape of the part that it's going to eventually become. And that plastic is just goes molds, open, and repeat. How fast is that process? Like, what does that look like from like in just a real time view?
Yeah, so a lot of it depends on part geometry, weight, material, but it can be as fast as 10 seconds, if not a little less. all the way up to 3 minutes, depending on how complex and how thick some of the wall sections are. There's things you can do post mold to help shorten some cycle times, but most of your benefit's going to come in a great part design and identifying those errors up front and getting rid of them for a quick cycle time.
Just add some efficiency there. Very cool. So we're taking that journey, and you talked about these BBs, this material.
Mhm.
What is this? Like, what type of resins or materials are used in injection molding?
Right. So we can use anything from really there's like 90,000 different types of plastic resins, different
Only
additives. Yeah,
90,000.
only 90. So you have ABSs, polycarbonates, more engineering grade materials like Ultem or PEEK, nylon 6,6, nylon 6,12, nylon 4,6. There's you name it. If you have an application, we can help you find the appropriate resin for your application. There's PBTs, polyesters, copolyesters, where there's a lot of stuff out there, and a lot of really neat applications for many different resins.
Awesome. And this material, it's usually like there's compounders, right, which are kind of work between these material suppliers, and they do things like adding colorant and
Mhm.
that sort of work. I mean, do you ever get raw material in the final color? Like, is it batched that way, or like how do I get more customization on the materials that I'm choosing?
Yeah, so there's a few things you can do. On a basic additive level, you can add things like UV resistance, which basically, if it's used outside all the time, you would want that to help prevent the plastic from degrading over time. You can use glass fiber reinforcements to help dimensional stability and structure, and increase the mechanical properties of the plastic. And then when it comes to color, you can there's a few different ways you can color the resin. You can do what's called pre-color, which is taking the color concentrates and the raw resin through a compounder, as you mentioned, re-extrude it and pelletize it in its colored form. That's the best way to ensure there's no color difference, batch to batch. Otherwise, you can do what's called salt and pepper blending, which you would basically put the raw resin and the color concentrate in a barrel, and you'd spin it or shake it up or blend it as best you can, and then load that into the machine. Other companies have what are called gravimetric feeders. This feeds the color concentrate and the resin directly at the machine at a specific weight ratio.
Those are pretty cool. Yeah, I've seen some of those devices, and that's kind of like the future of custom molding, right? Is being able to just very carefully at point change the pigment of your parts. I actually have a. You were talking about salt and pepper blending. It was really funny. I was in a molding area before, and I had someone looking into this barrel, and they're like, "What is this? What type of resin is this?" And they're looking around, and you could see kind of like the clear and the blue. And I looked a little bit deeper, and I was like, "That's ice melt. That's for winter. That's for our roads." And
Yeah,
because it was just happened to be like in the receiving bay, and they were, because they
yeah,
were saw these little beads with different coloration to it, and I
that's
was like,
great.
"Yeah, that's ice melt." But if you know what ice melt looks like, you may now know what injection molding resin looks
Yeah.
like before.
That looks more like a regrind material than it does raw resin.
Yeah. Well, now I have to ask. So we're talking about regrind. When you hear regrind, like what does that mean? What is regrind?
Yeah, so after the parts are made, sometimes there's a runner or sprue, which is how the material is conveyed from the nozzle of the machine to the actual cavity in the mold. You can take that runner and sprue and put it through a grinder and chop it up into and it's not really perfect pellets, but pellet size chunks, and you can reintroduce that into the molding
Hmm.
process.
Yeah. So I've seen some products where they say 10 or 20% regrinded. That's what they're talking about. So it's reusing some of the scrap material, which is very little of in injection molding, but there is some, especially if you have like these runners, these little pieces that you pop off. And reusing it within the material to, it's for both cost savings as well as being a little bit more, responsible environmentally
Yeah.
as well. So the one last question I have about material before it goes into, I think you mentioned before it goes into the hopper of the machine, right? So My last question is, often I hear about material going through a drying cycle.
Mhm.
Like why is material dried? Isn't it already dried when it's packed? Like why does it go through a drying cycle before it enters the injection mold?
Yeah, so some materials are hygroscopic, which means that they will actually absorb water, and water is detrimental to the injection process. Basically, when we are melting the plastic, it's above the boiling point of water, so it will create a steam in the injection process, causing a defect called jetting or splay across the surface. Not jetting, sorry, it is called splay, and that. That defect can be prevented by drying the material. Typical drying times are anywhere from 2 to 4 hours, depending on what kind of dryer you use. Um, and the temperature ranges will be specified on the material data sheets.
That and it reminds me very much like because I work mostly in applied additive manufacturing, and there's certain materials, particularly nylons,
Mhm.
that love absorbing moisture, and sometimes some of the defects you may see on your 3D print in nylons has to do with moisture absorption. So, in kind of a similar attempt, sometimes you are quasi baking the material to try to get moisture out, so drying it out. I've also seen some pretty cool applications where the material, as soon as it's used, is just held in a nitrogen environment with a little bit of positive pressure to just like so you just have clean, dry nitrogen in them. In that, if you have a nitrogen generator, like all of us do, of
Yeah,
course.
of course.
Uh, so it's interesting. Plastics are can be temperamental. That's definitely for sure.
You also have to take that into account. After the parts are molded, they're going to absorb water. Sometimes, as they absorb water, they can actually become more tough. They will also change in size. So you have to make sure that your quality system is aligned with when they're measuring parts and how they're measuring those parts.
Yeah, I think to that point, nylon I think does actually anneal and behave a little bit better with a little bit of moisture.
Yep.
And I've seen the reintroduction via a very fancy contraption after nylon molded parts are done, where they use a spray bottle, one spray into a bag, close up the bag, ship the parts. So very very fancy equipment there.
Of course.
That was actually in a major tier one automotive manufacturer, so it must work. All right, so we have this material dried, this resin plastic. It gets fed into the hopper, and you talked about this screw auger. So this is part of the injection molding machine, which is kind of encompassing. It's holding the tool. It's moving things around. Um, what what is happening to that plastic? Like what is happening between that hopper and right before it goes to the actual injection mold tool?
Yeah, it's going through a transition from being, solid pellets to being homogeneous melt. It is actually tumbling across and rolling around the surfaces of that screw and bouncing from the screw out to the barrel, where the heater bands are on the outside of the barrel. They're monitored. The temperatures are monitored with a thermocouple, so that heater band is either on or off at various stages down the barrel. 4 or 5 zones down the barrel is pretty common, and
Hmm.
those temperatures ramp up as you get closer to the nozzle.
Awesome. So, and I heard you mention in our conversation before, you said feed, transition, and metering.
Mhm.
Is that part of the auger process?
Absolutely. So the first part of that screw is called the feed location. That's where the raw pellets will fall into,
Oh,
and they're
okay.
not quite as melted. And then it goes down through that process to the tip of the nozzle.
I have to ask. So, say I'm running a fresh, like some new parts on my injection mold tool. I'm assuming my tool has been running other parts in it. How do you avoid cross contamination inside this auger? Like, can you look inside there? Can you access it? How do you remove old material?
Yeah, so there's some purging materials that are out there that will help scrape the screw and barrel,
Hmm.
and they can be in different material temperatures. So if you're using different materials can require different ways of purging, but you definitely want to clean that barrel and screw per industry standards before switching to a new material, and then you'll go through that process of purging to initiate. A good, consistent material going into your parts before making parts.
So I got. I'm purely curious on this. Would I ever be purging and doing any using the tool at the same time? Like, so would I use that to help like with my any feed rates or packing, or is that done in a separate process?
Yeah, so purging is typically a separate process. There can be different stages of
Mhm.
purging, right? So you can purge straight from the screw and barrel, and then if you have a hot runner or hot manifold system, you would want to purge through that as well. You'd want to purge through if you have valve gates or something attached to your hot manifold system. You want to make sure that you get as much new material, melted material, clean material in through that system before starting to make parts. You can still, even after you do all of that preparation perfectly, you may still see some contamination on the first few cycles. That's why it's strongly encouraged that you make 10 or 15 cycles of parts before
Yeah.
even keeping or looking at any parts.
And that's why, yeah. So once you have good parts, you don't see anything that's contaminating, like it's like a speckle of color or something. And then ultimately, those are going to be your initial samples or part of your production run for injection molding. That makes a lot of sense. All right, so we've taken material, we got the stuff, we've taken it through the hopper, we fed it through, we're up to the mold. First off, when I say mold, what are we talking about? Like, tell me a little bit about what it is when I talk about the mold or the mold tool, if you will.
Right. So there's two main sides of a tool. There's what's called the A side or the B side, the cavity side, the core side. The A side of the tool is attached to the stationary platen of the machine, and it's exactly that. It does not move. It stays right where it is. The other side of the tool will open with the hydraulics of the machine, and that's your splitting point, what's called the parting line of your tool. Uh, Inside
Okay.
of those, there can be slides or lifters to make minor undercuts or additional lines of draw, which would be ways that the cores or cavities may release from the part itself. Each one could be different, and there's different styles of molds. What we just talked about here would be a basically a two-plate mold. There's three-plate molds, which put a runner and gate drop system through an additional plate. Um, but each application has each tool, each part has its own requirements, and we can use those requirements to help design the best tool.
All right, so we have this tool. This tool has your core cavity, and actually, you're talking about the A side. Is the A side what's actually connected to the gate? So is that actually where the material is actually being fed through, or is it the B side?
It depends on what type of gate you choose, right? So if it's an edge gate, it very well may be half in the A side, half in the B side, or all in the A side, or all in the B side. It all depends on
Mhm.
the design of that tool and how it's going to release from the A side. We don't want anything to stay on the A side when the B side opens up. If the plastic stays over there, you then have to figure out a way to pull it off of there. There are some instances where you do what's called reverse ejection, where you purposely make it stay on the A side, but you've then turned your ejection system over to the A side of the tool as well, and you pull it with some hydraulics or some mechanical pulls to release the part. But like I said, each part, each geometry has its own challenges, and we can help navigate those.
All right, so all right, and we talked about. I kept on mentioning the gate. The gate introduces plastic, but that channel that's introducing. So the gate is actually the feature that introduces plastic to the part itself, and then you have the runner is actually what connects it to your screw auger that's metering and dispensing that material. Yeah, and you mentioned a little bit about this three plate molds and other things. So is that runner always existing in a part, and how is it removed? Like why don't I receive it on
Yeah,
my parts? When I get my
yeah,
parts in the
sorry.
mail.
There are a whole bunch of different gating systems and runner systems and valve gate system,
Mhm.
hot tip systems that may or may not require a sprue or runner that come out with the part. So if you're using a traditional gate or a runner sprue system, you will have a few different types of gate. You could have a cashew gate, you could have a tunnel gate, you could have an edge gate, a fan gate. And it just is exactly right. You are right. That feature that puts the plastic into the part itself is the gate. And there's instances that it will be attached to the runner sprue. Some of them are automatically degating, which means when the mold opens, and the part's ejected, the gate is broken off. That would be a tunnel gate. There's parts that the runner, the gate will be attached to the part. Those are edge gates, and those have to have a secondary operation to remove. It could be as simple as just grabbing it and breaking it off by hand, but it could be as detailed as having to CNC that part that gate off of there.
And so, I mean, I guess from your experience, what's most common? Like, so when we're talking about the gating and how to approach it, I know it's very geometry dependent, but what do you usually see? Like, so especially when we talk about potentially if I'm doing a low volume production versus production tooling, what options are you usually
Yeah,
thinking
so
about for a
we're
customer?
always going to push to try to identify the least labor, time sensitive option for you. But also as you do that, the tools may increase in cost. So if we're down and dirty, we just want the cheapest tool, and we're okay with some gate vestige. That's going to be the edge gate. It has its pros and cons from a injection standpoint. As far as supplying the part with enough plastic to pack it out appropriately. It may not be the most efficient from a cycle time. But if we can push more for an automatic degating system like a tunnel gate, those are relatively inexpensive. And if it's a low volume tool and you can get that, great. If it's a high volume tool, there are some maintenance issues that could arise, but it's definitely the next best. The most expensive and kind of the Cadillac would be a valve gate system, and that basically allows zero runner, zero sprue, and you basically turn on and off the plastic right at the part itself. It allows you to control gate seal immediately, and you basically pack the part out, shut the valve. It's a valve pin that kind of shuts off the gate and allow the part to solidify at that point. So uh, they're very complex, and it's a lot of fun though.
So is that when what you're talking about with that valve gate system? Is that also when I hear the phrase hot drop or hot manifold? Are those encompassing the same technology there?
Kind of. So the valve gate is actually,
Ooh,
yeah,
kind of.
kind of. The valve gate system is an addition to a hot manifold system. It's a few extra
Got it.
components that go into the valve system that have a pin that actually go in and shut off the plastic. Otherwise, your plastic would be open from hot tip all the way back to the hot manifold system. The valve gate allows a clean shut off between that.
Makes sense. And that's kind of like when you see a bunch of mass-produced goods, that's usually if I'm looking and I see like a little dimple shape or of some form on the part, and you don't really see any what we call that vestige. Like so that's basically where the ejection point is. Hopefully it's as mitigated or small as possible, but there has to be something there. But usually, if you see like an interior little dimple and maybe a tiny little dot, that's gonna show off where those type of systems are used.
Yeah, it very very well may be. If it's near the edge, it could also be a cashew gate because they will put that same dimple on a cashew gate with a
Oh yeah.
small little gate vestige right in the middle. So you can kind of see it on different gating schemes, but yeah, you're absolutely correct. Most of the time, if you see a bunch of them, that's going to be a hot drop system.
All right. So I have this plastic. It's molten. It flows into the tool. We are near the end. We are near the end here, and we were talking about these cycle times. Um, it is with this plastic cools. Is it really cool? Like, is it still pliable or is it the room temperature? And I guess what I'm asking is, what's going to stop it from like bouncing around or deflecting when the cycle is complete?
Yeah, so you want to make sure that the plastic is cool enough that the ejector pins won't push into it. That'll allow you to eject the part in the cycle time or in the cooling time of the part. You need to be you want to make sure that that process is done correctly. Different materials have different temperatures that happens at. For instance, if it's Ultim and it's being ejected off the part, you don't want to touch it. That's going to burn you very, very bad. It would never be encouraged to grab a part straight after molding. You have to be very cautious, and the appropriate PPE should be worn when handling those parts. But typically after the part is molded, depending on part thickness, it can be handled within 10-15 minutes.
That's awesome, and that's where you see it like being dropped on a conveyor, or it's often being collected and then going through any secondaries needs, or sometimes just packed and shipped away. Scott, any words of wisdom talking about this journey of plastics? We just covered everything from the material, going through the mechanisms of the machine, so going through the injection mold process, entering that auger, going and being metered and dispensed into the tool itself and into those cavities and cooling within the cavities. So we did an interesting journey from a very different perspective than I think like a lot of times when you're looking at injection molding as a process. Like any tidbits or any thoughts that we should talk about or
Yeah, I mean, there's a lot to plastic injection molding. There's a lot of variables. The best thing you can do is control your inputs, and that way you can have repeatable outputs. Follow the laws of plastics, right? So you want to make sure that you have uniform wall thicknesses, and you design your part appropriate for ejection and release from the A side of the tool, and identify your lines of draw appropriately, and that's really all I would have. And if you need any help, we're here to provide with some of that guidance.
No, absolutely. Scott, this is always a pleasure, and like I think it's something that there's so much mystery around injection molding. Yet it's also I'm looking in front of me right now, and I probably have 200 molded pieces of plastic just in front of me, like within a 2 foot reach. So it's such a common technology and manufacturing process, but there's always a little bit of mystery. It just doesn't just show up out of nowhere. Like there's actually stuff going on. So thank you for breaking down some of these topics. I definitely want to talk to you a little bit more. We mentioned molding part design, and I know that's something that's really exciting. And even things about molding finishes. How do my parts look shiny? How do they look matte? I think there's a lot of topics to cover there. For now, I think we'll close it there. Thanks so much for taking us on this journey of plastics through the mold, and Scott, really
Absolutely,
appreciate it.
glad to be here.
Manufacturing Explained is a Xometry production. Xometry offers instant quoting and over a dozen processes from 3D printing to sheet cutting to machining and molding. Xometry is your one-stop shop for manufacturing.